Chapter 26, Introduction, Part 1, Goodness of Fit. In Chapter 26, we return to categorical data and comparing counts and categories of data, such as we did in Part 1 of the course. There are three tests we conduct on counts of data. They're called goodness of fit, homogeneity, and independence. In this lecture, we're going to talk about goodness of fit. A goodness of fit test uses a representative sample drawn from a population of interest to determine whether or not the population is proportionally or disproportionately distributed among the various subcategories of a single categorical variable. Now, I'm posting the notes for this lecture online, and you can look them up or whatever. But anyway, let me repeat that. A goodness of fit test uses a representative sample drawn from a population of interest to determine, here, let's look at that. Let me look at that document here. Let me look at recent. Okay. Here it is. So you can stop this if you want to take notes on this or whatever, but this file is on Edline. So, a goodness of fit test uses a representative sample drawn from a population of interest to determine whether or not the population is proportionally or disproportionately distributed among the various subcategories of a single categorical variable. For example, so let's go back to the book here. Does it make a difference what your birth sign is, on how successful you are? Are successful executives the population of interest proportionally or disproportionately distributed among the various birth signs of the zodiac? Does it make a difference whether or not you're born under a certain sign if you become successful later on in life? So, a representative sample is taken from this population, a representative sample, random independent, not too big, not too small, of 456 Fortune 400 executives is taken and sorted by birth sign. Now here we get an example with baseball players. It's kind of interesting. I want to go back to the beginning here. Okay, so let's take a look at this. Okay. Now, here's an example. Genetic theory predicts that people have neither one or both of being able to curl their tongues and having attached earlobes. So they have 124 students in a biology class plan to collect data on themselves about tongue rolling and earlobes. And how many people should they expect to find in each one of the four groups? Well, they have the predicted fraction. According to the mathematics, 1/16, 3/16 1/16 should be non-curling and attached, 3/16 should be non-curling and free, 3/16 should be curling and attached, and then 9/16 should be curling and free, according to the information that was given in this table here. Okay, now, how do you figure out the expected amounts? You simply take the fraction times 124 for each one of these four subcategories. And we're going to do the same thing with the executives. Okay, what's our expected amount with these executives? Well, we're going to expect to see 1/12 of the executives in each cell. Okay, so 21.333% of the executives should be born under each sign. Now, how do we calculate the statistic? Well, the statistic consists of the observed amount minus the expected amount divided by the expected. Okay, let's go back to our document here. Okay. So, the test statistic is calculated by first calculating the expected count for each sign, 112 times 256. The difference of the actual and expected for each sign is squared and divided by the expected. The sum of these calculations for each sign, for each subcategory is generally referred to as a cell, is called the chi-square statistic, and it's symbolized by the italic capital X with the square next to it. So the chi-squared statistic equals the sum of the observed minus the expected squared divided by the expected. The calculation for one cell is called a component of the chi-squared statistic. Chi-squared joins all the other sample statistics we've worked with so far. So it's analogous to p hat delta, y bar delta, and d bar. All of these are sample statistics that we're going to run a test on, see how we're going to have hypotheses, and we're going to see whether or not the probability that we calculate on the statistic occurring, assuming the null hypothesis is true, we're going to see, we're going to evaluate that probability and make a decision. So let's do the test. Okay. All right, to do the test. Problem in context. Does a person's birth sign make a difference in how successful they are? Hypotheses. Null hypothesis. No, there's no symbols here. Okay. The count of executives for each birth sign is equal, as stated above. Birth sign makes no difference in how successful someone is later in life. The alternative hypothesis is simply birth sign does make a difference. These are the only possibilities for the alternative hypothesis. There's only one. Either your sample fits the expected categories or it does not. There isn't anything else. There's not less than or greater than or not equal to. Okay, assumptions. Since we are dealing with categorical data, this is something new, we must establish that the data is counts of categories. All right, so the numbers don't have units. The data is obviously counts of categories of birth signs. As the book states, if you look in the book, it says this should be a random sample. We're not told one way or another, and independence needs to be established. If the sample were random, then we could establish independence pretty well. Now this one, this is the establishment of whether or not the sample is big enough. Now this is similar to the rule that we have for proportional data, namely, we have a specific number. For the sample to be big enough, the expected cell frequency, not the actual count in the cell that we get from our data, but the expected cell frequency must be at least 5, which is 21.33. The sample is not too big. We're still following the 10% rule here, although later on we're going to talk about the fact that samples less than 10% of the population can be too big for the chi-square test, but we're not going to get into that right now. Let me get back up here. I skipped something. Okay, name the test. The preconditions are met. The chi-square statistic has a chi-square distribution of 12 minus 1 degrees of freedom. There are degrees of freedom here. The chi-square distribution, like the t-distribution, is a family of distributions according to degrees of freedom, which in this case, number of cells minus 1. So, perform a chi-square goodness of fit test. And now, test. Carry it out. You are not expected to write out all the calculations for the test, so we're going to go back to the calculator. Now let me make this smaller, not that small. Okay, bring this over here. And let's get the calculator in play. Alright, so make this a little smaller. Okay, so the first thing you're going to do is you're going to put in the expected amounts. You can either put them in L2 or in L1. You can put the actual count in L1, and the calculator actually expects your actual amount to be L1 and the calculated amounts to be in L2. I had them switched. So, but anyway, you can do it either way. It doesn't matter. You just have to make it. You have to adjust it when you do the test. So I put 21.33 in 12 times in L1, And then I put the actual counts for each zodiac sign in L2. Okay, and they're all there, and I double checked them and everything. Okay, now I'm going to go to Stat and Tests. Now you may not have this test on your calculator. If you don't, we will get it loaded on. Although it's not that hard to do manually. So we're going to do the chi-square goodness of fit test. D. I hit enter. Now, you will come up, you'll default to L1. If your observed counts are in L1, then leave this as L1. I put my observed counts in L2. My expecteds I put in L1, so I had to make those changes. Degrees of freedom for the goodness of fit test, it's 12 minus 1. It's n minus 1. Okay, so I hit calculate and I hit enter. And so here's my results, all right? Now, here's the chi-square statistic, which corresponds to the t-score and the z-score that I get from other tests. Okay, now it looks pretty big, 5.09, but this is a skewed distribution that's one-tailed. Now the degrees of freedom are 11, which means that the mode, the high point for this distribution is degrees of freedom minus 2. Okay, so this here I ran it for the drawing. So this is at 9 right here. Okay, and the mean for the mean, or is it the median? The median is actually the degrees of freedom. Okay, so this is given that information, this chi-square statistic of 5 is to the left of the mode and to the left of the median. So what that means is the area under the curve is really huge, almost 93%, a p-value of 93%. Now, okay, so this is a big p-value. Make a decision. Here, let's go. Sorry, let me go back here. The distribution of the chi-square statistic is always skewed right. The test is always one-tailed right. Okay, a p-value is a p-value. This one is way too big if we assume the standard alpha equals 0.05. We fail to reject the null. State the conclusion in context. The p-value of 0.93, we fail to reject the null. There is no evidence that zodiac birth signs have influence on a person's success later in life. Now, do problems 2 and 10. Use the book and the examples in the book and stuff. Also, I want to add in here, do just checking number 1, okay, and have them ready to turn in. Also. Well, you're not going to turn it. I'm going to look at it in your notes, but I want it in your notes. And then keep watching the videos. I'm going to send another one a little while after this one. And that's it.